Okay, we're in the home stretch. We're talking about the fifth and final section of lecture 11, finally getting to vestibular sense. All the rest was about hearing. So what is vestibular sense? So it is the sense of whether you are still or whether you are moving, and if you are moving, in what direction. It also is your ability to tell if you're right side up or upside down or on your side. Now, because the organs that we're going to be talking about in this lecture are in the head, it applies specifically to your head and where your head is moving and if your head is still or not. There are other parts of your body that can give you some information about what's going on there, but this is going to be confined to the head. So if you want to give your vestibular sense a workout, you can ride a roller coaster, right? So lots of movement happening there, lots of acceleration, deceleration, lots of going upside down, and maybe even if it's a spiral, right, you're kind of tilting side to side as well. So as you watch this, you may or may not start to feel a little dizzy or a little motion sick or feel like maybe you're on that roller coaster too. So I'm going to make it go away because it's annoying. But if that happened to you, know that it's because in order to figure out if we're moving or staying still, our brain is also using visual information. So what was happening right then is your visual information, if you were really locked in on that video of the roller coaster, was saying that you were moving, whereas your vestibular organs in your inner ear and other parts of your body were saying, no, we're not moving, which creates a very uncomfortable disconnect. Okay. So the vestibular organs are located in the inner ear. So we can see the cochlea here, our friend the cochlea for hearing. But the vestibular organs, vestibular sense organs, are these guys right here. So the semicircular canals and the utricle and saccule. And we're going to talk about them as semicircular canals and utricle and saccule because they do different things. We're going to start with the semicircular canals. So they are arranged in each of the three planes. So one is up and down, one is side to side, the other one is front and back. So let's see if I can do this. Up and down. I don't know if you can see it. Side to side and front and back. Okay, so much for my, the diagram's probably better. So much for my attempt at a visual aid. Okay, so these are filled with endolymph. We learned about endolymph. It also fills the cochlea, right? And it's going to sense rotation because if I tilt my head forward, then the fluid in the one that's going this way is going to move. If I tilt my head sideways, the fluid in the one this way is going to move. And then if I turn my head, right, this way or this way, the fluid in the one this way is going to move. So if I turn this way, turn this way, turn this way, right? So those different types of rotation are going to move the endolymph inside the corresponding canal. Now, at the ends of those canals, those semicircular canals, are little widened areas called ampulla, which you can kind of see here. Each one has an ampulla or a widened area at the end. And inside the ampulla, we're gonna find hair cells with stereocilia, which is so cool. So here are the hair cells, these little kind of pink cells here. And then we can see these are their stereocilia, I'm exaggerating, that are sticking up. And so as that fluid moves, the stereocilia bend, mechanically gated ion channels open, potassium moves in, which causes membrane depolarization, which causes voltage gated calcium channels to open. Calcium moves in, activates the snare complex, and you get exocytosis of the neurotransmitter glutamate. That should all sound very familiar, just like with hearing. And then signals get transmitted via an action potential down the vestibular cochlear nerve. Now you're like, why aren't you telling us whether there's bipolar cells or ganglion cells or whatever? It's unclear. They're still doing research to figure this out. And also we have to draw the line somewhere. So just know it goes into signals along the vestibulocochlear nerve, cranial nerve 8. What about the utricle and saccules? So these also have endolymph, but they have these little rocks, these little calcium carbonate crystals that are called otoconia specifically. So just in general, if you have these little calcified rocks anywhere in the body, they're called otoliths, but specifically these are called otoconia. So you'll see the words used interchangeably in the text, which is unfortunate. So the way this works is, again, we have hair cells with stereocilia, and we have a membrane in this kind of gelatinous cap, and then you have these otoconia. Now the otoconia are heavy. So you can see in the diagram here, if you tip your head back, they're gonna kind of sag down, and then that's gonna pull on the stereocilia. So this allows us to sense gravity, right? Because if I turn my head this way, now my otoconia are falling this way and bending my stereocilia that way, right? But it's also going to allow us to sense acceleration because of inertia. So I think that's the next slide. I don't know. We'll see. Nope. Almost. So one is oriented so that you can sense horizontal, and the other one so you can sense vertical tilt, right? So you've got the two different directions there. I remember it as the utricle is for horizontal, so that's how I remember it, UH. Okay, so acceleration is going to cause the same physical manifestation as tilt. So this is the diagram that you saw before. So now I'm just going to add a person and they're accelerating, right? Imagine they're in a car that's going shoom, right? And when that happens, right, you know how you feel like, you know, there's this inertia and it takes a little while for the things in your body to catch up with you. Well, the same thing is true for the otoconia. So the otoconia like hang back and cause the stereocilia to bend on the hair cells. So acceleration causes basically the same exact physical response in the otoconia as tilt. And so because of that, you can kind of trick your brain, because it's very hard for your brain to tell the difference if all you're relying on is your utricle and saccule to know the difference between tilt and acceleration. So that's how those rides work. I love Disney World, and so I love Star Tours, where it's like a Star Wars thing, and you go into this little shuttle and you sit down, and there's a giant screen in front of you that's supposed to be like your, windshield basically, and then you fly through space and all kinds of things happen. Now, the way they make this work and feel really realistic is that whole little shuttle that you're in is actually on a series of mechanical things that are going to tip and tilt you. So when you're seeing an image like this, where you're, accelerating and flying through space, it tilts you backwards. And so that information combined with the visual information that looks like there's stars going past you, it totally feels like you're flying through space. Really fun. But sometimes it's not so fun if everything doesn't line up. So motion sickness is something that occurs when your brain is getting conflicting information. If your eyes are telling you that you're moving, but your vestibular system and your body senses are telling you that you are not, that is very confusing for the brain, and it tends to make you motion sick and nauseated. So earlier when you watched the roller coaster, your visual sense said motion was happening, everything else said it wasn't, and so that may have made you feel a little queasy or a little uncomfortable. On the opposite side of things, if you're on a bus or in a car and you're reading something and that thing is in front of you, and so what you're looking at is staying still, but your body is moving, especially if there's a lot of acceleration, deceleration happening, there's a lot of bumps in the road, those types of things, it's conflicting information. Some parts of your body are telling your brain that you're moving, others are saying, nope, visually, nope, I don't detect any motion whatsoever, and that is what causes motion sickness. So in summary, the vestibular sense, we've got two different types of structures in the inner ear. We have the semicircular canals oriented in each plane, and so they're really good at sensing rotational movement, because that fluid then will end up in the ampulla where it bends the stereocilia on the hair cells. The utricle and saccule use otoconia so that we can sense gravity, and we can also sense the inertia that occurs when something accelerates, because the heavier thing will take longer to catch up. So they're really good at sensing both gravity and position, or gravity to tell us our position relative to the gravitational field and acceleration, but they're not good at telling the difference between the two. And so they can be tricked, especially with strong visual stimuli. And anytime we get mismatched stimuli about where we are in the world, in space, whether we're moving or still, that can cause motion sickness. All right, that's it for lecture 11.